Modern robots for agricultural automation are controlled far too conservatively and often have unnecessary number of actuators that drive up cost and frequency of maintenance. We investigated the eminently practical triple pendulum cart pull to pick apples and reduce the number of actuators required. Initially, we used LQR to balance the triple cart pull at its upright position. However, we want the system to be able to reach the unstable equilibrium point from any arbitrary initial state and handle obstacles, such as tree branches. We investigate 3 methods for doing this. We used 2 different value iteration approaches. The first approach was a discrete mesh-based value iteration. Because it suffers from exponential computational complexity, we only applied it to the single pendulum cart pull. Here we plot 2D slices along the cost to go function we found via this method. After 40 minutes of iterations, it converged on a policy that was able to swing up a cart pull. Note that this policy is global and can swing up for other arbitrary angles. Here it swings up from a 90-degree starting angle, and here it restabilizes after being pushed over. Our second approach, we used a neural net to estimate the cost to go function. This didn't suffer from exponential computational cost, but it was nonetheless difficult to tune, and it did not achieve a swing-up controller. Some limitations. For discrete value iteration, we want to pay extra attention to the regime close to the fixed point to ensure it stabilizes there, but we didn't sample our input states more densely near the fixed point. For our neural network, our hypothesis class was a fully connected neural network. The paper by Letter et al. Shows that narrowing the hypothesis space for control affine problems such as this enables it to fit the true cost to go more easily.
Here we look at reachability-guided, rapidly exploring random trees. RRT is a method for finding a path through state space that goes from a starting state to a final state. On the left, I show the RRT algorithm for 2D path planning around obstacles. On the right is the result of running the same algorithm but constrained by the dynamics of a torque-limited pendulum. RRT star is a modified RRT that progressively refines the tree to find the lowest cost solution to any given point. Results here show RRT star applied to both the 2D setting with obstacles as well as the dynamically constrained pendulum swing-up problem. Reachability-guided RRTs provide more efficient state space exploration. They do so by restricting the randomly sampled region of state space to only that which can be progressed towards in some time step. By doing so, they drastically reduce the number of nodes needed to reach some goal. LQR stabilizes the trajectory and helps correct for any linearization errors. LQR also smooths out the input torques, as you can see in the torque and theta graph. Our reachability-guided RRT converges on a solution substantially faster than RRT, but there is still a lot to be desired. RRT failed to find a swing-up trajectory for the cart pull or triple cart pull within any reasonable time frame to be a reliable online solver. This is most likely due to an inefficient implemented tree algorithm in conjunction with the high dimensionality of the problem state.
So now finally we look at trajectory optimization. So in this case we formulate the control problem as a nonlinear mathematical program where we've set the final cost to be equal to the total time, where these h of n is the duration between any 2 breakpoints, and then u is the input force on the cart, and we can also apply a cost to that as a running cost. The main constraints are the dynamics, which imposes a nonlinear constraint, and then we specify the start and end goals that we want, and we apply some constraints on the distance of time between the breakpoints. So when we also apply a constraint on the position of the cart, with these boxes you can see in the animation, we can find an input force trajectory, and then we can plot the states over time. However, if we actually plot what the input force would be if we commanded it to the cart, we see that the cart falls down. And in this graph on the right, you can see the cart deviates from its nominal trajectory. But with finite horizon LQR, even with small deviations in the initial starting position of the cart, we were able to get it to stabilize to the target position. And then we're also able to add additional constraints using forward kinematics and basically putting in different distance constraints that each of the masses of the pendulum need to be away from, for example, like a tree branch, and we can avoid these obstacles. And while this approach was successful, we found that it was difficult to tune the many different parameters required for both trajectory optimization and finite horizon LQR. Overall, of the 3 methods, we found trajectory optimization to be the most tractable.